Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper 6 exam for May-June 2016, variant 1. So let's get started. Question 1 says a student is determining the weight of a meter rule using a balancing method. The apparatus is shown in figure 1.1. Part A says the student places a load P on the meter rule at the 5 cm mark on the left here. She places the meter rule on a pivot at the 45.0 cm mark. She places load Q on the rule and adjusts its position so that the meter rule is as near as possible to being balanced. So Q is on the right side. She measures the distance x between the center of load P and the pivot and the distance y from the center of the load Q to the pivot. She repeats the procedure, placing the load P at the 10 cm mark, at the 15 cm mark, and 20 and 25 cm marks, and the readings are shown in table 1.1. Part I says for each value of x, calculate A equals P times x, where P is 1 Newton, so 1 multiplied by all these values. So basically they are the same number, so 40.0, 35.0, 30.0, 25.0, and 20.0. Then for each value of y, calculate B, which is equal to Q times y, where Q is equal to 0.80 newtons, and record the values in the table. So we multiply 0.8 by these values. First one would give a value of 34.0. Next we have to make it all one decimal place. So 0.8 times 36 gives approximately 28.8. Next is 24.0. Next is approximately 19.2. Actually it's exactly 19.2. Next we have 14.0. Double I says complete the column headings in the table. So we had the distances in centimeters, so x and y are in centimeters. And for P and Q, the unit is Newton, and then they were multiplied by x and y, which were in centimeters. So we have units Newton times centimeter, so Newton centimeter for A and B. Part B says plot a graph of A per Newton centimeter on the y-axis against B per Newton centimeter on the x-axis, and start both axes at the origin. So first we label the axes A per Newton centimeter here, and we have 5 divisions, B per Newton centimeter here, and we also have 5 divisions. As for A, the maximum value was 40 and the minimum is 0, since we have to start both axes at 0. And then we divide by 5 divisions. That gives an answer of 8. Comparing with 1, 2, and 5, all these are less than 8. So we take the first one and we multiply it by 10. And this is our scale, 10, 20, 30, 40, and 50 at the top. As for the x-axis, the maximum value was 34.0 and the minimum value is 0. And then we divide by 5. That gives an answer of 6.8, again greater than 1, 2, and 5. So we do a scale of 10 on the x-axis as well. So 10, 20, 30, 40, and 50 at the end. And this is our scale. Now we plot the points. First point from A is 40 and B is 34. So 40 and 30, 1, 2, 3, 4. This is the first point. Next we have 35 and 28.8. So 35 is here and 28.8 is approximately at 29. So just before 29. This is the second point. Next we have 30 and 24. So 30 here, 21, 2, 3, 4. Third point. Next we have 25 and 19.2. 25 is here, 19.2 just after 19. So at this point approximately. Last point we have 20 and 14. So 20 and 11, 12, 13, 14. It's here. Now we see if the first and last points make a straight line best fit. Yes, it's almost going through all the points. We continue the line. So we will most probably be asked to get the y-intercept here. Part C says using the graph determine the vertical intercept, which is y-intercept, for A at B equals 0 Newton. So this point here, we have 6 divisions. This is 6.0. Not everyone will get the same exact point. This is my graph. And the unit on the y-axis is Newton centimeter. Part D says calculate the weight W of the meter rule using the equation W is equal to Y over Z, and Z is 5. So 6.0 divided by 5.0. That gives an exact value of 1.2. And here we had Newton centimeter, then we divided by centimeter, so these cancel out and we have the unit Newton. And it also said weight, which has the unit newtons. Part E says suggest one practical reason why it is difficult to obtain exact results with this experiment. This experiment has a famous problem, which is it is difficult to make the rule balance horizontally. It usually tips to one side. Part F says the student uses an accurate electronic balance to obtain a second value for the weight of the meter rule. The weight obtained on the balance is 1.24 newtons and we had 1.2 newtons. State and explain whether the two values of the weight agree within the limits of experimental accuracy. So the difference is less than 10% or less than 15%, so we say yes. And you say that the difference is only 0.04 newton, or too small or very small, or within the limits of experimental accuracy. Question 2 says the student is heating water in a beaker using an electric heater. Part A says he measures the potential difference V across the heater and the current I in the heater. Write down the readings shown on the meters. So for the voltmeter, we have 5 divisions between 8 and 9, so each division is 0.2. So this is 8.2 volts. And for the ammeter, in the middle here we have 0.5, and this is exactly in the middle between 0.4 and 0.5, so it is 0.45 ampere. Part B says he measures the temperature of the water before heating. Write down the temperature reading theta shown in figure 2.2. So this is just before 20, this is 19 degrees Celsius. C says on figure 2.3, draw a line and an eye to show clearly the line of sight required to read the volume of the water in the measuring cylinder. So we draw a horizontal line at the bottom of the meniscus, and the symbol for the eye is drawn like this, curves only. And you can mention that this is 90 degrees. And of course it is from the side of the scale, not the other side. Question 3 says a student is investigating the resistance of a lamp filament. The circuit is shown in figure 3.1. We have a power supply, a switch, and a meter connected to a slider on a resistance wire. And the position of C can be changed to measure distance D between A and C. And we have the lamp in series and the voltmeter. Part A says the student places a sliding contact C on the resistance wire at a distance of 0.200 meter. From point A, he measures the current I in the circuit and the potential difference V across the lamp. He repeats the procedure using the values of D of 0.4, 0.6, 0.800 meter, and the readings are shown in table 3.1. First, I says calculate the resistance R of the lamp filament for each set of readings and use the equation R is equal to V divided by I. So we divide this column by this column. So 1.6 divided by 1.00, this gives an answer of 1.60 or 1.6. Next we have 1.3 divided by 0.86, that gives an answer of 1.51. Next we have 1 divided by 0.74, that gives an answer of 1.35. Last one, 0.8 divided by 0.66, that gives an answer of 1.21. Double I says complete the column headings in the table. So the distance was mentioned in meters in the question. Potential difference is in volts, current is in amperes, and the resistance is in ohms. Part B says the student notices that the lamp does not glow when he takes the final set of readings. He thinks that the filament has broken. State whether the student is correct and give a reason for your answer. So the last set of readings does not glow, but there is still current in the circuit, which means that the lamp did not break since everything was in series. If the lamp breaks, everything stops and the current is 0. So the statement is not correct or false. And the reason is that there is current in the lamp, so it is still working, but just not enough to make it glow. Part C says the student suggests that the resistance R of the lamp filament should be constant, suggests referring to the observations, a reason why the resistance R may not be constant in this experiment. So for the observations, we have the measurements of voltage, current, and distance, and we have the appearance of the filament lamp. So very bright, and dim, and not glowing. That means that the temperature is different. So the resistance here differs as the temperature differs. We can say that the filament brightness changes, which means that the temperature changes, and that may cause a change in resistance. Part D I says name an electrical component that could be used instead of the resistance wire AB and the sliding contact to vary the current. To vary the current, we have a variable resistor. Double I says draw a diagram of the circuit including this component instead of the resistance wire and the sliding contact. So we can redraw everything except for the resistance wire. We had a power supply, a switch, and a meter. And from the left side we had the lamp with a voltmeter connected in parallel to the lamp. And now we draw the variable resistor in series instead of the resistance wire. And then we close the circuit like this. Question 4 says a student is investigating the effect of insulation on the rate of cooling of hot water in a 250 cm3 container. The student can choose from the following apparatus: thermometer, 250 cm3 glass beaker or plastic beaker, copper can, measuring cylinder, 3 different insulating materials, clamp, boss and stands, and a stopwatch. Now we are required to plan an experiment to investigate the effectiveness of 3 insulating materials, so these are the independent variable. You should explain briefly how you would carry out the investigation, state the key variables they would control, draw a table or tables with column headings to show how you would display your readings. You are not required to enter any readings in the table. Explain how you would use the readings to reach a conclusion. A diagram is not required, but you may draw a diagram if it helps your explanation. So we can draw a beaker like this on a horizontal bench, a stand with a boss and a clamp to hold the thermometer. So we draw it like this, and the thermometer we can just draw it as a line with a circle at the end or a dot at the end. We have the liquid here, and we can just draw any rectangles from the outside like this, and this is our insulation. And then we label everything. So we have here thermometer, clamp, stand, we have insulation on the outside, we have the beaker on the inside, and we have hot water in the beaker. First we can say heat water to a certain temperature, then pour water into the glass beaker. Then we can say set up apparatus as shown in the diagram using the first insulating material. Now for the rate of cooling, we say measure the initial temperature and start a stopwatch. Then we can say measure temperature theta every 30 seconds, and you can say for example 180 or 120 seconds. Technically the experiment is done, but we need to repeat the experiment for the other insulating materials. So we say repeat all steps for the other insulating materials, but we mention some controlled variables. So we say use same beaker, initial and room temperatures, and same amount of hot water in the beaker. We didn't mention any precautions, so we can mention them separately. So precautions: look perpendicular to the scale of the thermometer, or we can say stir before reading. So stir water before reading temperature to make sure that the whole liquid is at the same temperature. As for the table, we can place the time per second on the left side, and we have the temperature per degrees Celsius for material 1, material 2, and material 3, and we close the headings like this, and we do not enter any values in the table. We just leave it with column headings and with the units for the temperature and time. Now to compare, we plot a graph for time per second on the x-axis against theta per degree Celsius on the y-axis for all materials or for the 3 experiments, and compare gradients. As a controlled variable, we can also say use the same thickness of each material as insulation. Question 5 says a student determines the focal length of a lens. The apparatus is shown in figure 5.1. The student places the lens at a distance u from the illuminated object. He moves the screen until a sharply focused image of the object is seen on the screen. On figure 5.1, measure the distance u from the illuminated object to the center of the lens, and also measure the distance v from the screen to the center of the lens. So first u, this is 5 centimeters exactly, but the unit here is in millimeters, so we write it as 50. 5 times 10. Now for V, this is 2.1 centimeters, so it is 21 millimeters. Figure 5.1 is drawn 1/10 the actual size. Calculate the actual distance U capital from the illuminated object to the center of the lens. So we multiply 50 by 10, since it is already divided by 10. That gives us 500 millimeters, and we multiply 21 also by 10 to get V. So that's 210 millimeters. Double I says calculate the value f1 for the focal length of the lens using the equation f1 is equal to uv over u plus v. So 500 times 210 over 500 plus 210. That gives an answer of 147.88732, so on. This is approximately 148 millimeters. Part C says a second student repeats the experiment 3 times using a different lens. His values for the focal length of his lens are shown in table 5.1. Calculate the average value f2 for the focal length of this student's lens. So we add the values 132 plus 141 plus 135, then we divide by the number of readings, 3. That gives an exact value of 136 millimeters. Part D says a third student using the same method finds that the focal length f of her lens is 200 millimeters. She reads in a book that when u is equal to 2f, the distance u and v as shown in figure 5.1, which are the distance from the lens to the screen and the distance from the lens to the illuminated object, are equal. So v should also be 2f. First we need to calculate the value 2f. So f is 200, so 200 times 2. That's 400 millimeters. The student sets up the apparatus as shown in figure 5.2. She adjusts both x and y to be 400 millimeters. So this is the theory that x and y should be equal to each other instead of u and v. She observes that the image is blurred. It is not focused, so the theory may be wrong or there might be some errors. The student slowly increases the distance y and obtains a sharply focused image when y is equal to 406 millimeters, not 400. Discuss whether the student's results confirm the statement in the book. So 6 millimeters compared to 400, that's a very low percentage error. So we can consider them to be the same number. So we say yes, they support the statement or the theory, since the difference between 406 and 400 is within limits of experimental error or experimental accuracy, which should be about 15%. Part E says suggest 2 precautions that you would take in this investigation in order to obtain reliable results. We can say perform the experiment in a dark room so that the image would appear better. We can say place rule as close as possible to apparatus or look perpendicular to the scale. We can also say use pointers. We can say make sure the center of the lens and the object or the illuminated object are on the same level or height. So this was the end of the exam. I hope you enjoyed this video and found it useful to you. Keep practicing and I will see you in another video.